So welcome back, everybody. We hope you had the chance to check out our recruiting booths, student demos, and research poster presentations. If you haven't already, please make sure to vote for your favorite research poster on our Google Forms. That's linked in the reception area or in any of the research booths at the expo. There will be a link that says vote for my poster, and you'll be directed to the Google form to do that. So next up, we will be starting our second chapter, information. By the way, what does that mean? Let's think of one of the biggest revolutions in the past century, the internet. Able to host this very conference is by passing signals between our devices which travel at the speed of light. The devices we're using are performing millions of computations per second, powered by nanoscopic transistors. The way we interact with, compute, and convey information today is largely powered by nanotechnology and will be the topic of focus over the next hour. That brings us to our next segment, the computing panel. I would like to welcome to the stage our panelists, Dr. Stephanie Simmons, Dr. Heiner Linke, and Dr. Sylvain Gigon, along with our panel moderator, Dr. George Chulevsky. And I guess just to preface, so we have been having a few errors with our connectivity, and so I'd just like to point out that Hopin might want to consult with some of our computing experts here on how to build a very robust platform. So forgive us for the time being, and I'll leave it to George and the rest of the panel.
Okay, thanks so much, Ethan, and thanks so much for organizing such a great session today. So again, I'm George Chulevsky. I'm a research scientist and a program director at IBM Research in Yorktown Heights, New York. I'm generally interested in nanoelectronics and materials for electronics. And our research division is broadly interested in advancing silicon technology, quantum computing, and developing new devices and architectures for AI workloads. And I'm really delighted today to have three respective leaders in their field who all are working on advancing the state of the art in computing research, but in three very, very different ways. So I thought first I'd start off by introducing our three speakers and then giving them a minute or two just to kind of give us a broad view of their research interests. So I'll begin with Professor Stephanie Simmons from the Department of Physics at Simon Fraser University. She's also the founder and the chief quantum officer of Photonic Inc. So let's start with Stephanie. So Stephanie, can you tell us a bit about your research interests?
Yeah, sure. So I've been motivated by the goal of harnessing the next generation of physics. And we talked about, or what was mentioned by Ethan, thanks for everybody setting this up. We talked that information is nanoscopic, but information is physical. And right now we're using information kind of contained by the laws of classical physics. And once we can start taking a look at the laws of quantum physics, we can open up a lot more opportunities. So what I'm doing is I'm building quantum computers. Right now our lab is the only one, our labs are the only ones that are looking at silicon with memory and telecom access. So that's kind of our niche, and it's going pretty quick. And so I'm happy to talk about all of that, but basically it's a really exciting space. As you know, everything's accelerating, and it's a lot of fun to be a part of it right now. I'll leave it there, George.
Hey, thanks so much. Next, we have Sylvain Gigon, professor of physics at the Sorbonne University in Paris. He's also leader in the laboratory of Kastler-Brüssel at École Normale in Paris as well. So Professor Gigon, could you please tell us a bit about your research interests and the activities going on in your group?
Sure, thank you. So yes, so I'm broadly interested in optics and photonics, and my group has been working for about 10 years on the optics of light in complex media. And this started mostly for imaging, because tissues are complex media and everything around us is mostly complex, like paint, clouds, and so on and so forth. But in the last 5 years, we realized that propagation of light in complex media can emulate some operations that are interesting for optical processing. And so we've been working on this since then, and more or less in two directions. So the first one is really classical optical computing, which is to perform optically large-scale matrix multiplication And so we are working on different way to do that in the lab, like reservoir computing, recurrent neural network, and different tasks. And we have also a startup that has now 20 people working on a real life application of this kind of optics. And we're also doing a little bit of quantum computing, like photonic quantum computing, like propagating states, photonic states in such complicated networks, and trying to apply this for simple tasks. So I'll also stop at that for the moment.
Wonderful, thank you. We'll get back on detail as well in just a few minutes. And finally, we have Professor Heiner Linke, who is the director of NanoLund, the Center for Nanoscience at Lund University. So Professor Linke, could you please give us a brief summary of your group's research interests?
Yeah, so well, first, thank you very much for having me here, and I hope the connection works. My video seems to come and go. So I've been interested in a long time in molecular motors, so the type you find in biological cells or that power your muscle, for example. So those are proteins that convert chemical energy into mechanical motion. They can walk and push and produce things like copy DNA and or RNA or make proteins. And a little bit through serendipity, I got interested in how to use them in context of nanotechnology, so how to move things around in nanochannels, for example. And it turns out that one real exciting application of this is parallel computation. So there are NP completes or combinatorial problems that really need a lot of steps to be taken. There is no speeding up. You sort of have to perform a lot of computations to find the answer. And those are a challenge for serial computers. So those are the examples they're often also used to motivate quantum computation. And it turns out for many of these, you can convert the mathematical problem into a maze. So you can imagine you build a large complex set of channels, and the solution to your problem is encoded in that. So if you explore all the possible paths through the maze and, for example, find a specific exit, then you have the answer to your question. And molecular motors can be used to solve such mazes, and the key thing being that they are super energy efficient. So the molecular motors are very much optimized by evolution and can perform a computational step at about 10,000 times less energy than a transistor. So there's a possible pathway to energy efficient parallel computation.
That's wonderful, thank you. And then again, we'll talk a bit more about that, specifically the last piece in detail in just a few minutes. So I want to get a little bit deeper into each of your work. So Professor Simmons, let's just start with you. So quantum computing has attracted an enormous amount of attention, both in the scientific community, but also just in the general public. And I think there's pretty broad agreement as to the value and the impact quantum computing will have, let's say in materials discovery and chemistry and certainly certain optimization problems. But I guess what's not totally clear is what the underlying technology is going to be, or what it's going to look like. I mean, at IBM, we're very focused on superconducting circuits, and there are many groups working on that, but there are also, ion traps and quantum dots and photonic devices. And I just want to get your point of view and your perspective on, kind of the path the community is on to kind of shake out what is the right device for this emerging technology. And if you could also comment on the role that nanotechnology and material science, maybe more broadly, is going to play in that journey.
Yeah. So, I mean, it's interesting that you heard the term software eats the world. I mean, just from the panelists around here, quantum computing is going to eat the world next. It seems like everybody's jumping in. So yeah, you're totally right. It's definitely gathering pace in terms of attention as well as progress. But I also want to touch on one of your original points. Yeah, it's perhaps agreed that it's going to be super valuable, but we do not have the collective imaginations to know how big this is going to go, right? Like we're at the stages where we're basically at the transistor stage, to your point about what kind of the hardware is going to look like. And trying to explain, Facebook to somebody in the 40s is going to be a completely different thing. So we don't know how far this is going to go. And every single time you unleash a branch of physics to the commercial side, it just goes crazy. So to your point specifically, you wanted to ask about the various hardware. So let's just take a look at those past trajectories, right? Let's take a look at when electricity went from being magical to mainstream, or even what was talked about, the internet, like all the technologies that gave rise to the internet, the rest of them. There's a language for what the process looks like. Actually, everybody gets really excited, and then there's this mass proliferation of different approaches, right? Like dozens of different approaches that all come up and compete. You saw this with phones and microwaves and like anything, no matter what the scale, you get like all these different variety, and then it has a mass consolidation event actually. And so the term that's used in the business industry or the business literature is dominant design emerges. And then all of a sudden everything kind of shakes out and settles out. So at the moment we're at that stage, right? Like it's not quite clear what the dominant design is going to look like. From my perspective, the reasons I have bet on the horse that we're riding right now is basically if you ever bet against silicon and you don't end up doing very well. So silicon is like, to your point, right? IBM has been in this game for a long time. Silicon will win if you can get it to work, just because we understand it better. Like it's not a complicated system. It's understood to death, right? So I'm working on the motivation that silicon will win. It'll be networked, right? Like all of our computing powers, you're gonna have networks, so you're gonna have telecoms. And you're going to have some memory applications for it. So, I mean, that's why we're working on the technology that we are. But I mean, when the consolidation event happens, it's going to be a really, really fun ride to see how that goes, right? Everything changes on a dime. It'll be a lot of fun. And you said about materials and asked about that. So there's even though it's still silicon, it's not like everything's done, right? There's still a lot of work that you'd want to do. But if it is silicon, then you can stand on the shoulders of giants and really benefit from decades of research there. If you want to have more exotic stuff, then there's a lot more materials work to be done to bring that to a commercial setting. So there's definitely a role to play for some of those other technologies, and as well as silicon to a degree. But I don't need to get into the details there. I'll leave it there.
Right. So you mentioned a consolidation event where basically everyone recognizes this is the device, this is the foundational
this or something like it. Yeah.
So what triggers that? What sort of what boxes have to be checked for us? Do you think will have to be checked for the community to consolidate around whatever it is, one specific type of qubit?
Yeah. So
what are the key
attributes? It's not going to be just the technical ones. It will be a combination of technical and psychological, as well as commercial, right? So it can be on a technical front if there's like orders of magnitudes difference in performance. In which case there are, right? Between the different qubits, there are really, truly orders of magnitude difference in performance on a number of different metrics which matter, right? So that's one. The other one is just like kind of fashion, right? Like if you have 95% of the people developing one thing, even if it's not the best technology by a factor of 2 or something, you would expect still that consolidation to happen around there, right? So it is psychological in that front. And the last one's cost, right? At some point, there'll be a consolidation, but then it'll kind of start shaking out on, who's going to make the most money off of it. And some of those things really do matter, right? Like it gets down to commercial things. So we're still at the stage where even the technical stuff isn't really understood very well in terms of what those metrics, like how, because everybody's pushing their own metrics, right? So it's a lot of fun. It's a lot of fun, but it's good. We're trying to learn the lessons of history, right? Like that's where I see it going. So.
Yeah. I think the last time you touched on this idea that everyone's using their own metrics. There really isn't an agreed upon benchmark to measure these devices. And that's going to be some really interesting work I think the community is going to have to do over the next, 5 or 10 years to have an agreed set of benchmarks.
Yeah, but what are the metrics for AI? The metrics are at work, right? So you can come up with whatever proxy metrics you want, right? And so people, you can put numbers to anything that's measurable, but ultimately it'll come down to what's useful. And so if there's consensus in just like a fashion sense, like this one's useful, then that's where it's going to go. Mm-hmm. Right. And so, you can try and put a number to it, and that can be helpful. And people want that, right? It gives some kind of clarity. It gives us some sort of like comfort, like when we're working on something that's competitive. But, it's and so those will exist, but I don't think they're the full story.
Yeah. Okay. Well, I think it's going to be a really exciting and interesting and probably unpredictable decade to come for just the field in general.
Well, there's room for everybody. That's
yeah.
the broader sense. Right? Like it's a lot happening, and there's room for everyone.
Yeah. I think it's a great comment to leave that question on. So I'd like to move on. Let's go to Professor Linke. So you talked about energy efficient compute, and looking at the semiconductor industry, what's really enabled Moore's law to happen is constant field scaling. This idea that as you make the transistors smaller, they consume less power. Otherwise, you can never have, a billion transistors on a chip. And pretty much every technological advancement in silicon, whether it's high-K dielectrics or FinFETs or nanowires, or even these sort of more exotic exploratory materials, the motivation is to drive towards low power, higher performance devices. So, and I think maybe it's evident or it's well known, but the reason that Moore's law is, at least one of the major reasons that Moore's law is slowing down, is the fact that we can no longer scale the power at least as efficiently as we could over the last several decades. And so you're taking a radically different approach to addressing this power issue, and I know you alluded to it a bit in your opening summary of your work. But if you spend a few more minutes telling us about how you and your team is addressing this power issue using this very different form of compute.
Yeah, so thanks for this background. I think, maybe just is Moore's law ending or not? I think there's the size issue, of course, but as you said, one thing that is very clear is that it has been some time since processors actually sped up. The gain in computing power in the last years has mainly been due to using multiple cores in parallel, because we haven't been able to, in a significant way, getting around problems of power dissipation, so heat overheating, or speeding up, and those are tightly connected to one another. Maybe first up, before I explain a little bit more what we are doing, is that I do not expect that the technology we work on will ever replace the type of computers that we have now, because they will be for something entirely different. What we do, so just to explain this a little bit more, is we take certain combinatorial problems. So this is a term for problems that require you to go through a vast amount of different possibilities to find the right solution, and encode them in mazes that then are explored by these molecular motors. So we code nanochannels that form the maze with a motor called myosin or kinesin. Those are two different options. And then have them propel filaments. This can be actin or microtubules, which are in the cell, their walkways, so to say. So by tying down the motors, the filaments will move. So it's a little bit like crowd surfing. And it's very smart because the motors will only operate when their substrate is there. So if there's no filament, they just sit idle and don't do anything, don't use any energy. And in that way, we can then solve, or we have done small instances, so there's a long way to go in terms of scalability, but we can solve combinatorial problems. And the key is we are interested in problems that for large instances are really difficult to solve for even a supercomputer at the moment. And this is not going to change in the foreseeable future, because even if you build bigger supercomputers, the power consumptions of these things is gigantic. So you run into some real, apart from the obvious climate issue, you also run into some very serious power supply issues. You basically need a nuclear power station next to a supercomputer if you're going to go much, much bigger than they are now. So the vision is to be able to solve problems that otherwise are simply not solvable, but not problems that occur when you load Facebook on your mobile phone. So I don't expect that technology to change. And I fully agree that will be silicon or maybe some hybrid version of silicon also in the future. What I also don't expect is, so what we are working on is entirely classical. So the niche of, say, quantum simulations, which I see as one of the important niches of quantum computation, that is also something we will never be able to do. On the other hand, there is reason to believe that quantum computers actually will not be great at solving these combinatorial problems, and there could be a niche for biocomputers. But it will be replacing technology and always in combination with other computation technologies.
Great. So you, just out of curiosity, when you sort of create these you refer them as mazes, right? That allows you to do the problem. So does each problem then need its own maze designed and fabricated to solve, or is there some kind of programming that you can do?
So that's a very good question. And at the moment, we are sort of at the proof of concept. We are scaling up, but from starting from a low level. We have not developed the ability to program in the sense that the mazes we use so far are indeed hardwired. So you hardwire one specific problem into the maze. It's totally imaginable to do programmable mazes. So basically, our mazes consist of channels that cross and have intersections, and we sometimes literally use roundabouts. And there are traffic rules that we somehow need to geometrically enforce so that the filaments know what to do. It is totally imaginable that one could use with electric gating, or we play around with heat. So for example, you can have thermally responsive polymers that either block or don't block the motors, and thereby you can turn on and off certain sections by applying local heat. You could imagine the same with local light. So there are certainly ideas for how to make them programmable, and clearly sustainable technology will strongly benefit from that. But I'm not even sure it's absolutely important, because the vision is to be able to solve problems where, because you cannot solve them mathematically right now, like protein folding, you actually have to make one protein after the other, solve the structure, understand its function. So entire pharmaceutical R&D departments work on that. So if you could short circuit that process, even if that means you have to make one bespoke device to solve one specific problem, it would potentially still be a huge gain in time and resources. So yes, we are working on programmability. No, we haven't solved it yet, and I don't think it's the critical part, maybe.
Oh, very, very good. So we're talking about power dissipation and power consumption. I want to continue that theme, but shift over to Professor Jigan. So, obviously AI workloads are becoming very dominant in IT, and I think maybe what's not obvious to non-experts is the power consumption that is needed to do these modern AI workloads. There's a really interesting graph that was published by OpenAI about 2 years ago. It's very easy to find on Google, but they plot year versus total compute, and they put these kind of hallmark AI achievements like AlphaGo and AlphaZero and some of these transformer algorithms. And you can see that the compute needed to execute, to train these algorithms grows exponentially. And it's very clear that it's unsustainable. These models are getting very large. The amount of data that you need to train them grows as the model grows. And to Professor Linka's point earlier, there's the issue of climate. I mean, you're just obviously burning a huge amount of energy to train these algorithms, but also at some point it just outstrips our compute capability. It just becomes too expensive computationally to do these. And so it's very clear we need more efficient algorithms, but also more efficient hardware. And I've seen a lot of work on people use GPUs now. There's sort of next generation GPUs that are like low precision silicon devices. There's even some work on analog electronic devices. But Professor Jigan, your group looks at sort of optical devices to address building more energy efficient hardware for AI workloads. I'd love for you to tell us a bit about that.
Sure. So of course, I fully agree. So we know that AI needs are, I think that the number I had in mind is that they are doubling every 3 months. right? Which is to compare to Moore's law, that is not, of course, in action at the moment, but that was every 2 years. So it's growing very, very fast. And so what people need in this algorithm is to do a lot of matrix multiplication, and typically, and also they have a problem that information from the memory to the CPU to compute, and this transfer of information, which is getting bigger and bigger, is also becoming a huge bottleneck. So it's the so-called von Neumann bottleneck of conventional computers. So in a way, conventional computers are not made to perform this operation efficiently. And this is why several platforms, and in particular optics, have been considered to do this operation a bit more naturally. So what we do in our case is that the medium itself, in a way, operation for you. So the light propagates it, and there is some multiplication from some kind of input modes, which are basically pixels that we control on a modulator to a camera. And it really goes from millions of modes at the input that we have on display typically to millions of modes at the output, which are basically detectors like CCD and so on. So if you put the numbers in, you see that you have basically 10 to the 12 operation that you can repeat at kilohertz typically, or several kilohertz. So you have at the same time 10 to the 15 operation per second, which is a lot. And this is basically to answer your question. But also you don't need to move information from a memory to a compute to a processor, because the matrix is the medium itself. So there's no need to transfer this information. So this is, I think, a big advantage of the kind of platform that we propose, and that of optics and photonics in general, that you have these two basically for free and at a very low energy cost, because the propagation is for free. You need a little bit of energy to operate modulator and detectors on each end, and the lasers, but that's typically relatively low. So also, I would like to say, because you spoke about the algorithm, that in this case you also need to take you need a new hardware, and so we have this kind of system. We have also basically also spiking neural network neurons in solid states, and similar technology that allows to do also some neuromorphic computing. But I think you also need to have algorithms that are just adapted to this hardware. So sometimes you also need to find the right algorithm that match better this hardware. So this is also something very, very important that I think will be needed in the future.
Great. And
so yeah, I'll probably stop there
just to
for
follow
now.
up. So you talk about in-memory compute. So the logical element itself stores some information. I'm guessing it's a weight or something with the neural network. So in the electronic devices, this is done by varying the resistance. You just build like an analog device where you can modulate the resistance very easily. What's the I don't want to say analog, but what's the optical version of that?
Yeah, that's a very good question, and there is actually a catch. So in what we do, in my case, the matrix is huge, so it's really 10 to the 12 elements, but it's basically fixed and random. So in a way, we cannot tune it. We can tune other things, but not the matrix. And this is why we need some specific algorithm designed for this random. It's called random projection. So there is a lot of algorithm based on that, but it's not the mainstream algorithm. Other photonic approach can do tunable, but then they are much lower scale. So the approach we push at the moment is this large scale random connections.
Mm-hmm.
But yeah, is that answering your question?
Yeah, no, absolutely. So we're at the top of the hour. We have about 10 minutes left in this panel. I want to remind the audience, I am watching the event chat. So if you have a question for any of our panelists, feel free to type it into the chat panel. I should have told you that earlier. So I hope, so again, all of these scientists are working on advancing the state-of-the-art compute, but you can see it's sort of coming at it from really radically different directions. So I hope that you students in the audience see that kind of as Professor Simmons mentioned earlier, there's a lot of work to be done, and really everyone is welcome. And whether you're a material scientist or say electrical engineer or more on the algorithmic software side, you all have valuable contributions that you can make to these fields. As we alluded to earlier, Moore's law silicon will continue to do its thing, but certainly the gains that we received in the past are saturating. I mean, that we can say for certain. So there's really a great opportunity to develop completely new modes of computing, new devices and architectures, so that we can keep at least the technological advancement moving at the pace it has been, even if we're not relying on one single technology like we have in the past. So with that, I just want to move on to kind of a couple more general questions. So most of our audience is students. We were all students at one point. So I would love for each of you to answer a couple of questions. So I want to go around and maybe you could tell us, say one or two key moments or decisions between when you were an undergrad and where you are now that you think were really critical to put you on the right path. And then maybe give one piece of foundational advice that you would have, say, given to yourself when you were in the position as most of our audience was in. So I'm going to start with Professor Simmons with this final set of questions.
Sure. So pivotal moment, it was pre-undergrad. I read in a local news, I'm a Waterloo person. I grew up in Waterloo. So for those listening in the audience, we get your winters. I get it. I'm living in Vancouver now for a reason, but I get your winters. I read an ad in the local paper when I was just turned 16. They're going to start this Institute for Quantum Computing. And I thought it was the most amazing thing. I had no idea what it meant, but it just sounded like the most amazing thing. So the turning point for me was just exposure, right? I mean, like, everybody kind of has that thing that clicks for them. And the reason that you guys are listening to this conference as students is because presumably a moment like that happened in your past, right? Like, so you're like, oh, this technical thing, this sounds cool. Let's go explore. It's almost never the case that what first excites that is the thing that carries you forward all the way to the end, right? Like, so I'm quite on this when I talk to people about this, like that I just stuck with the first thing that really caught that, ignited that. So what I can recommend in that vein, this isn't my words of advice, but this is something that I would take home from it. Exposure matters a great deal, and expose yourself so much more broadly than you think you'd be interested in, because a lot of the times there's reasons why people get into what they're looking at, and oftentimes it's really hard to see that from the outside. You have to kind of get into it a little bit to understand why people would even be interested in it. So I would highly recommend expose yourself as much as possible, and that means like live internationally, like move, and think very carefully about who you're going to work with as a supervisor more than the institution, because the supervisor plays a really big role, and I'm not sure we actually tell our undergrads that very, very well. So I guess that would be the bit of advice I would give is definitely take a look at who the supervisor is and do the hard thing. What you offer is if you are able to do the hard thing and like just don't shy away from doing the hard thing, you become a very, very scarce resource, and then you become highly valuable. So I mean, don't do it to the point where you're self-destructive, but like, I'd say give it your all, and you'll do very, very well. It's not necessarily one choice or the other makes a big deal in your life. If you have a personality that touches on that, then I think you'll do. I'll leave it there.
Thank you. Yeah, choosing a mentor. This just to echo this. You're right. This is not something we teach our undergrads about, and how important it is to find someone that you share a vision with and are simpatico with, and it's probably the most important relationship you'll have as a student. Is who your mentor,
right?
Is who your mentor is.
But yeah, it really matters. It really matters so much more than the brand of the institution. Like the brand of an institution helps, but it's absolutely about people. Even in a really high technical field, it's all about people. So about who you're linking with and who you're learning from and how well they can communicate to you and how well like they set you up. It matters a great deal. And then who you're surrounded by, right? Because you have to live with what we're doing on a day-to-day. You want to be enjoying yourself, right? So
certainly. Great. Okay, let's go to Professor Linke. So again, a couple of key, from the perspective of the students that are watching us, some key moments and some one piece of foundational advice that you would have given yourself. I don't hear you. Are you on mute?
Yeah. Oh, sorry about that. Pivotal moment ties directly back to Stephanie's advice to expose yourself broadly. I did my PhD in low temperature semiconductor physics, so the type of stuff that's now called quantum technology. Back then it was a really basic physics, and even though we said it would at some point be used for future of computing, we didn't actually think that was the case. At least I didn't. So when I went to like meetings like the APS, I would listen around very broadly and just take my time to look into other stuff. And at some point I got into statistical physics session where they were talking about how to use thermal motion and random motion to get directed work out. And I learned about these molecular motors that somehow did that in biology. And in those days, it was early stages of trying to understand how that works. And that fascinated me and put me on the path where I'm now. I've stayed with semiconductor physics, but I built this other leg of exploring the physics of ratchets, the physics of random motion, how to get that to work, and got involved with this molecular motor crowd. The advice, I'm not sure how good advice it is for others, because that is now a little bit in conflict with Stephanie says. I myself have never tried to plan a career or to pick a mentor based on career prospects. I fully sign up on find persons, work with people that you think you like to work with. I fully sign up on that. I have strongly followed my interests. I literally chose to do a postdoc in Australia, not because it was the best group there, but because there was a group and it was in Australia. That was what I was interested in. But the people I met there, they stayed colleagues. I still have multiple partners who I closely collaborate with who go back to that time. And that has shaped my career for sure. So I personally would more give the advice, follow your interests. Don't follow where everybody is rushing right now. But if you find something that you are really interested in, that excites you, that's worth sticking with. And a bit about find people that you like working with, that you share values with, and that you personally enjoy working with. The mix of those two, I think, works for me.
Yeah. Well, I mean, frankly, I don't think you're too far apart.
No, we're not.
The way I hear you describe it, but yeah. Again, I mean, interests. Finding, again, I don't want to repeat myself, but again, finding people that you're simpatico with and that you want to work with and you share a vision and values with go a long way to being successful. So last 3 minutes, let's move over to.
Sorry, I know I'm going to be rude here. Just to be the counterpoint, it's actually more advice to the counterfactual, right? It's make sure to avoid the really bad supervisors, because I've really that's really more what the point is, because bad supervisors can torch careers of geniuses. So just that's all. But I wanted to be the more upbeat side.
Yeah. We all know who they are, so that's good. All right, Professor Jigan, we'll leave it with you again. A couple of key moments and some foundational advice.
Yeah. Thanks. So yes, I'm actually, maybe there's a bias of people trying to follow a bit of an unconventional approach to computing. So we all like to basically very important. So I switch topic a few times between PhD and postdoc, not too much, and then after postdoc quite a lot. my career also quite a lot, like 5 years ago. And this also came from meeting people, meeting new people, and really from completely different disciplines. So for me, I'm also coming from fundamental physics, and I met these people from machine learning, signal processing, and I learned a lot. It was really every time a tremendous boost and a tremendous experience. So it's really narrow-minded and keeping an eye open for new collaboration, exciting connection between what you do and what other people are doing. That's very important. So I would really encourage to keep that in mind when doing research.
Okay, great. So I think we are just at 10 minutes after 2 Eastern time. I want to thank our 3 panelists for a really interesting conversation. You heard a lot of diverse and interesting research topics, and I think some really great advice. I want to thank the organizers, and especially Ethan Thompson, for putting this panel together. He's very thoughtful in his selection. I think it was a great discussion. So I hope everyone enjoys the rest of the conference, and I hope we can all congregate in person the next time we have to do this. Everyone be safe and be well, and we'll see you soon. Thanks, Ethan.
Thank you. Great. Yeah, just to echo what you said, thank you. It was truly amazing, amazing conversation spanning 3 time zones. So thank you so much for your insights into these new computational methods. And I think this may be the first time we get to hear all of these perspectives in one place. So I think that was a special conversation for all of us, for sure. Thank you all very much.
Thanks a lot.
Thank you.
Great. Take care.
Thanks a lot.
And so we arrive at our last part of the information chapter, which is our breakout sessions. So in the sessions page there, again, for those of you who have been here already since the morning, you know that there are 2 choices for you for breakout speakers. We have 2 amazing speakers working in different areas of nanotechnology and information. We have Dr. Shide Ameri, who will be talking about her research at Queen's University on 2D materials for biosensing, wearables, and human-machine interfaces. We will also have a breakout from Qinshu Wang, who is a graduate from the Nano program at Waterloo, and who will talk about the interactive light field displays he is working on at Avalon Holographics. So again, both very interesting topics, so there's no wrong choice here. So right now, we can disperse, go to our preferred breakout session, and then I'll see you again here at 3:15 for Dr. Robert Langer's keynote address. All right, see you soon.